Okay, so our next speaker is Vikram Ravi of Caltech. Vikram is going to tell us about fast radio burst science progress and promise.
Excellent, thanks Chris. And yeah, thanks to the organizers also for allowing me to give this talk. So I'd like to tell you a little bit about fast radio bursts, or FRBs, and especially for this audience, it's worth saying a little bit about how we detect them and how we discover them. So they're observed in really high time resolution radio surveys around the gigahertz bands from roughly a few hundred megahertz to a few gigahertz. And these data look like this. And so in time series of spectra, we observe these swept frequency signals where the delay that increases to lower frequencies tells you that these bursts are definitely extragalactic. And this is because the delay is caused by dispersion in plasma along the line of sight. And so because the dispersion is much greater than expected for the Milky Way ISM, we can actually infer distances of something like a few gigaparsec in some cases at a few hundred megaparsec, and so on. So in more recent times, as in this is such an amazingly fast evolving field that I feel like every time I give this talk, I sort of say something different when I say what's happening recently. We now know of the population of over 100 FRBs, of which something like 10 have secure host galaxy identifications. FRBs are characterized by being roughly milliseconds in duration, have extremely high energy outputs, their apparent luminosities, as you can see from this plot of duration versus the spectral luminosity, are comparable to HEM for the millisecond they're on. And we observe them with immense volumetric rates of somewhat over 10 to the 5 per cubic gigaparsec per year, which for the supernova aficionados is higher than the supernova rate as well. We think that the likely sources are these highly magnetized neutron stars, potentially pulsars, but probably something a bit more exotic like magnetar. And this opens the possibility of really exotic origins. How do we form the full population of magnetars in the universe is one question that some fast radio burst scientists hope to answer. There are currently no associated transients at other wavelengths, although we recently discovered a galactic fast radio burst analog that was actually coincident with an X-ray burst from a known galactic magnetar as well. Now, FRB host galaxies tend to vary wildly. I'm plotting them here in stellar mass versus star formation rate, and you can see these large stars are the FRB hosts, some of which are shown here. And you can see that they largely lie along the star-forming main sequence. Credit to graduate student Chris Bochenek for this plot. But certainly there's a lot more work that needs to be done to fully understand how FRB host galaxies sort of can tell us about the kinds of progenitor populations. And so at Caltech, we are trying to build an array of 110 radio dishes at the Owens Valley Radio Observatory. This is called the Deep Synoptic Array. And this will, when complete by roughly the middle of next year, localize more than 100 FRBs per year to host galaxies. So with accuracies of less than about 3 arc seconds. The idea is to have a core of about 95 antennas, several outrigger antennas to provide the precise localizations, and we will send out alerts to the community within 60 seconds of each localization. So what do we want to do? So I guess from this stage onwards, I'd like to project forward a little bit into the future, taking some case studies as motivations. And so it seems as if the progenitor problem will likely take several tens of events to actually be solved. Of course, there will be some transformational discoveries like this galactic FRB that I mentioned, which by being traced back to a known magnetar said something about the mechanisms by which FRBs are generated. But if you think about other examples of transients like short gamma ray bursts, it took several tens of events plus events like GW170817 to really nail down the progenitor and emission mechanism. But at the same time, what I'd like to leave you with is this idea that it's becoming really clear that FRBs, much like quasars, are actually fantastic probes of intervening gas. Not so much like GRBs potentially, but certainly FRBs are being used to say a lot about the gas in between galaxies, the intergalactic medium, gas surrounding galaxies, the circumgalactic medium, as well as potentially the ISM of the host galaxies as well. And none of this will be possible without excellent optical data. So I think one of the examples that I'd like to show you is this burst that we detected with the prototype of the Deep Synoptic Array, the DSA, just a 10-element array that I put together as a postdoc at Owens Valley, where we identified an FRB. You can see down here a series of frames showing the detection of the burst in an interferometric image. Using Keck, we identified a host galaxy at redshift of 0.66, and we're able to show that it was much like the Milky Way in its stellar mass and potential star formation rate as well. But what's turned out to be even more exciting than that, in my opinion, is the actual field of this FRB, where what we show here is the host galaxy itself, and what we found is that between the host galaxy and us lay this pair of intervening galaxies at roughly half the redshift. But then in the background was also this distant and relatively bright quasar. And towards this quasar, we were able to detect magnesium-2 in absorption, both at the redshift of the FRB host, as well as at the redshift of this intervening pair. You can see the detections here. And what this allowed us to do is to actually compare the H1 and ionized hydrogen masses through these halos. And this has allowed us to say that there really aren't incredibly massive reservoirs of hot, so greater than 10 to the 5 Kelvin or so gas along these sight lines. And I'm comparing here various detections from Jeff's work's 2014 COS halos analysis, comparing the total column densities with the neutral hydrogen column densities, as well as the constraints we get from this FRB sightline. This is certainly preliminary work, but we hope that there is a significant potential for similar studies in the future. One other bit of work I want to highlight, led by my postdoc Dana Simard, is where...
So, Vikram, let's wrap up so we can have a chance for questions, please.
Sure thing. So I just want to highlight this idea also that FRBs can say a lot about multipart propagation through the host galaxy ISMs. And we hope that we can link these probes on scales of roughly AU to scales of kiloparsec that we can get from, for example, velocity dispersions. And so just to conclude, it seems as if we have a clear path forward. We will need tens of FRBs with both good spectroscopic and photometric coverage of the host galaxies to say something about the progenitors. We will need probably a few more than a few tens of FRBs to dissect the IGN and circumgalactic medium baryon contents. And to probe these structures across a range of scales, we will need medium to high resolution spectra of just a few host galaxies. And I'd also like to leave you with this thought that the optical transient sky on these timescales is also wide open, and it probably requires extreme sensitivity to make progress. Thanks.
So thank you. We have time for a question if somebody wants to type it out. And while they're typing, I'm going to ask, how did you get so lucky as to have a quasar projected behind one of your initial discoveries of a...
Yeah. I mean, it's roughly a 1 in 50 chance, I think.
Oh, you did well then. So there was a question, is the DSA triggered by other facilities? If so, how quickly do you need to follow them up and localize them in real time?
No, so DSA both discovers as well as does the localization. So we discover and then localize post-processing.
Okay, very good. So there will be time for other questions for Vikram in the Slack channel.